Howdy. This video is on the basics of electrochemical reactions. There are many electrochemical reactions, including the formation of rust, combustion, and many reactions in biological systems. All reactions where an element's oxidation state is an electrochemical reaction, meaning electrons are transferred from one element to another element. We'll be able to rank an element and compound's ability to either gain or lose electrons, and hence its reactivity. And so after watching this video, you should be able to assign oxidation numbers to elements and compounds. You should be able to identify what is being reduced and what is being oxidized in a reaction, as well as the reducing agent and the oxidizing agent. You should be able to identify electrochemical reactions. You should be able to determine how many electrons are being transferred in a reaction. And so in Bronsted acid-base theory, it was all about the transfer of hydrogen ions. Whatever lost the hydrogen ion was the acid. Whatever gained the hydrogen ion was the base. Electrochemistry is about the transfer of electrons. And so in this reaction, we have copper going to copper plus 2, and so the copper is losing 2 electrons. The silver ions going from a plus 1 to a silver metal, and so each silver is gaining 1 electron. 2 electrons that the copper is losing is exactly equal to the 2 electrons that the silver gains. And so electrochemical reactions, you just have a transfer of electrons from one thing to another thing. And so electron transfer reactions have a reduction, something is gaining electrons, and has an oxidation, something's losing electrons, and so they're often referred to as redox reactions. Redox, electrochemical, I'll use those interchangeably. So redox reactions can result in the generation of electric current, or can be caused by imposing electric current, or actually neither. And so again, remember that rust and combustion are redox reactions, even though you don't have any current present. And so for redox reactions, you have an oxidation. Now oxidation is when something's losing electrons, and so you have an increase in oxidation number. So electrons are negatively charged. Oxidation number is a charge an atom would have if the bonds were ionic. And so if something loses its electrons, it's going to have an increase in oxidation number because the electrons are negatively charged. Reduction is the gain of electrons. Electrons again negatively charged, so if you have a gain of electrons, your oxidation number is going to go down. Now the oxidizing agent is what causes the oxidation. And so oxidizing agent is always reduced. Reducing agent is what causes the reduction, and so reducing agents are always oxidized. Now you can remember oxidation reduction using Leo goes Gur. Lose electrons is oxidation, gain electrons is reduction. Now originally oxidation meant to form an oxide. Now oxidation just means to lose electrons. And so if we look at copper plus oxygen forming the copper oxide, and so that's what we mean by forming an oxide. So the copper is being oxidized here. It's going from oxidation state of 0 to a plus 1, so it's losing an electron. The oxygen is being reduced. It's gaining 2 electrons. And so copper loses electrons and hence is oxidized. Oxygen gains electrons and hence is reduced. Again, for electrochemical reaction, you always will have something being oxidized and something being reduced. And copper forms an oxide by transferring electrons to the oxygen. Atoms and molecules are often characterized by their oxidation number or oxidation state. I will use oxidation number and oxidation state interchangeably, or by their formal charge. Now, the oxidation number is the charge an atom would have if the bonds were purely ionic, and it's useful in tracking electrons. Formal charge is the charge an atom would have if the bonding electrons were equally shared. Formal charge is useful in determining which structures are more stable, which Lewis diagrams are more stable.
The common oxidation numbers of the elements exhibit periodic trends. For example, the common oxidation numbers of the alkali metals are all 1, while for the alkaline earth elements of group 2, they are 2. These values correspond to the numbers of valence shell electrons in the atoms of these elements. As we move from left to right across a given row, the maximum oxidation number observed increases regularly to +7 at manganese. From lithium to boron, the commonly observed oxidation number increases from 1 to 3. Carbon can have more than one oxidation number. For example, -4 in a covalent compound such as methane, CH4, +2 in a compound such as carbon monoxide, or +4 in a compound such as carbon dioxide. Nitrogen similarly has several different oxidation numbers in the various compounds in which we find it, ranging from -3 in a compound such as ammonia, NH3, to +5 in a compound such as nitric acid, HNO3. The more electronegative elements, oxygen and fluorine, show only negative oxidation numbers in their commonly observed compounds. The elements of the third row of the table show a similar variation in oxidation numbers. Notice that the most positive oxidation number observed for each element increases steadily in moving from sodium to chlorine. Notice that chlorine and sulfur have positive oxidation numbers. These occur in oxides and fluorides of these elements, because chlorine and sulfur are less electronegative than oxygen and fluorine. In the fourth row of the table, we encounter the first transition metals series. Notice that the maximum oxidation number increases regularly to manganese. As we move beyond manganese, the most common oxidation states for the transition metals are +2 and +3. For the nonmetals in this row, the observed oxidation states are very much like those of the corresponding
second row. And so please remember, oxidation number, oxidation state, same thing, is the charge an atom would have if all the bonds were purely ionic, all the bonds in the molecule. And so in general, the maximum possible oxidation state is equal to the charge an atom would have if it lost enough electrons to get noble gas configuration. And so for nitrogen, it loses 5, so 1, 2, 3, 4, 5, it will have a noble gas configuration, so the maximum oxidation number for nitrogen is 5. For carbon, if it loses 4, 1, 2, 3, 4, that would give it a maximum oxidation state of +4. Now notice this is not usually true for the transition metals. There are transition metals where you have those d orbitals, d electrons, are a little bit more complicated. Typically, the minimum possible oxidation state is equal to the charge an atom would have if it gained enough electrons to get noble gas configuration. And so for fluorine, if it gains 1 electron, it gets noble gas configuration. And so its minimum oxidation state is a -1. Oxygen, if it gains 2, it gets noble gas configuration. So its minimum is -2. Now again, notice that this is a little bit different for the transition metals. Most elements exhibit a range of oxidation states. Which oxidation state they're in depends on what they're bound to. And so if you look at chlorine, chlorine can go from a -1, so if it gains 1, it gets noble gas configuration, to actually a +7. If it lost 7, it will get a noble gas configuration. So a very wide range of oxidation states. For carbon, it can go from a -4. If it gained 4, you get noble gas configuration. If it lost 4, it gets a noble gas configuration. And so carbon can have a -4 through to a +4 oxidation state. And again, its actual oxidation state depends what it's bound to. So in a compound, alkaline metals will have a +1 oxidation state, alkaline earth will have a +2. You can be really pretty confident of those two in a compound. In a compound, fluorine will have a -1 oxidation state, oxygen will have a -2, and hydrogen will typically have a +1 oxidation state. And so you can be pretty confident of those three. And so you can be fairly confident of knowing the oxidation states of the alkaline metals, alkaline earths, fluorine, oxygen, and hydrogen in a compound. When elements are by themselves and have no charge, they have a 0 oxidation state. And so in a compound, fluorine is typically a -1, but F2 gas, fluorine has a 0 oxidation state. In a compound, oxygen typically has a -2 oxidation state, but O2 gas, the oxygen, will have a 0 oxidation state. In a compound, magnesium will have typically a +2 oxidation state, but magnesium metal by itself, you have a 0 oxidation state. And so in general, the maximum oxidation state corresponds to the charge an atom would have if it lost enough electrons to get noble gas configuration. So in general, the minimum possible oxidation state corresponds to the charge an atom would have if it gained enough electrons to get noble gas configuration. Most elements exhibit a range of oxidation states. Which oxidation state they're in depends on what they're bound to. So in a compound, alkali metals will have a +1, alkaline earths +2, fluorine -1, oxygen -2, hydrogen +1. And so you can be fairly confident of those. And then elements by themselves with no charge will have an oxidation state of 0. And so there's actually two ways to determine oxidation states. The first way is using two rules. And then the second way is drawing the Lewis diagram. Now, using the two rules works 95% of the time, is much faster. I strongly recommend that you try using the two rules first. And then if the two rules don't work, you'll notice, and then you can try using the Lewis diagram. But the two rules is much faster than the Lewis diagrams. And so the first rule is you can be fairly confident of oxidation state of a few elements: fluorine, oxygen, alkali metals, alkaline earths, and hydrogen. Now again, remember that we say in a compound, fluorine has oxidation state of -1, but when it's by itself, it is 0. Now the second rule is that the sum of the oxidation states of the elements of a compound equal the net charge of the compound. And so when you're using this rule, you always start with the elements that you are most confident in knowing, the oxidation states. And you just make sure that the sum of the oxidation states equals the net charge. And again, the two rules work 95% of the time. It's much faster than using the Lewis diagram. And so I always suggest you first try the two rules. And so if we want to figure out the oxidation state for the carbon and oxygen in carbon dioxide, we can start with the two rules. And so the sum of the oxidation states equals the net charge. And so we have 2 oxygen, so 2 times the oxidation state of the oxygen, plus the oxidation state of the carbon equals the net charge, which in this case is 0. Now we can be pretty confident the oxygen is a -2. So 2 times -2 gives us a -4. And so that means that the carbon must be a +4 oxidation state. So this is how we use the two rules. The sum of the oxidation states equals net charge. If you have 2 oxygen, you have to multiply the oxidation state of oxygen by 2. We're confident of oxygen. Remember, we can be confident of fluorine, oxygen, hydrogen, the alkali metals, and the alkaline earth. Carbon can have oxidation state of +4 through -4, and so we're not sure what it's at. And so we use the oxidation state of oxygen, the net charge, to actually determine the oxidation state of carbon. And so the two rules much faster than using Lewis diagram. Now if we want to do the Lewis diagram method, we start by drawing the Lewis diagram. Now remember that oxidation state is the charge an atom would have if the bonds were purely ionic. And so what we do is we draw the structure as if the bonds were purely ionic. And so oxygen is more electronegative than the carbon, and so the oxygen gets all the bonding electrons. And so now we have that. And now we just go, the oxidation number equals the number of valence electrons of the free atom. And so for carbon, it's in the 4th column. And so the atom of carbon will have 4 valence electrons, minus the number of valence electrons in the bound atom, with the bonding electrons to the most electronegative. And so now carbon has 0. So 4 minus 0 gives us a +4 oxidation state, the same as we found using the two rules. For oxygen, it's in the 6th column. And so you have 6 valence electrons for the free atom, minus 2, 4, 6, 8. Minus 8 gives us a -2, and we would expect oxygen to have a -2 oxidation state. And so again, we see that the sum of the oxidation states equals the net charge. Oxygen is more electronegative than carbon, hence the bonds, if the bonds were ionic, oxygen would get the bonding electrons. And notice that the more electronegative element gets the negative oxidation state. The least electronegative element gets the positive oxidation state, because the most electronegative element gets the bonding electrons if you assume it's an ionic bonds. We can try another one. So here we have methane. And so for the two rules, we have the sum of oxidation states equals net charge. And so we have 4 hydrogen plus oxidation state of carbon equals the net charge. Now the net charge here is 0. Oxidation state of hydrogen is typically a +1. So 4 times 1 gives us 4. And so that means the oxidation state of carbon in that compound must be a -4. Now, we can try it using the Lewis diagram. And so we can start with the Lewis diagram. Again, the bonding electrons go to mostly electronegative. Carbon's more electronegative than hydrogen. Now we can go number of valence electrons of the free atom. And so that would be 4 for carbon, -2, 4, 6, 8. And so we get a -4 for the oxidation state of the carbon in this compound. For the carbon dioxide, we had seen that carbon was a +4 oxidation state. For hydrogen, we start with 1 valence electron for the free atom, -0. And so we have a +1 oxidation state like we would expect for the hydrogen. And again, the sum of the oxidation states equals the net charge. And carbon is more electronegative than hydrogen, and so we would expect the carbon to have the negative oxidation state. And so for the carbon dioxide, oxygen's more electronegative. It gets a negative oxidation state. Carbon's less electronegative. It gets the positive oxidation state. For the methane, carbon's more electronegative than hydrogen, and so carbon gets a negative oxidation state, and hydrogen gets the positive oxidation state. And again, we saw that carbon, if it lost enough electrons to get noble gas configuration, it would have a +4 charge, and so +4 oxidation state. If it gained enough electrons to get noble gas configuration, that would give it a -4 oxidation state. And so carbon can have any oxidation state from +4 to a -4. We can try one more. And so here we have the ammonium ion. It's got a +1 charge. And so the sum of the oxidation states equal the net charge. In this case, our net charge is a +1. And so 4 times the oxidation state of hydrogen plus oxidation state of nitrogen has to equal a +1. So 4 plus oxidation state of nitrogen equals 1. And so that means the oxidation state of nitrogen must be a -3. We can do it using the Lewis diagrams. And so again, we start with the Lewis diagram. Nitrogen is more electronegative than the hydrogen, and so the nitrogen will get the bonding electrons. Remember, oxidation state is a charge an atom would have if the bonds were purely ionic. And now we just do number of valence electrons of free atom. So free atom of nitrogen has 5. Here we have 2, 4, 6, 8. And so that gives us a -3 oxidation state for nitrogen. And for hydrogen, it is a +1. And again, the sum of oxidation states equals the net charge. And again, the more electronegative element gets the negative oxidation state. The least electronegative element gets the positive oxidation state. And so using 2 rules, you should be able to determine the oxidation states for all these. And so silver is by itself, has no charge, and so it should have a 0 oxidation state. Copper has a +2 charge, and it's by itself, so it should have a +2 oxidation state. Remember the second rule, the sum of the oxidation states equals the net charge. And so the net charge here is that +2, so the oxidation state of copper must be at +2. Here we have ammonia, so oxidation state of nitrogen +3 equals 0, and so nitrogen must be a -3. So oxidation state of chlorine -2 equals -1. And so oxidation state of chlorine must be a +1. For this one, we got a +3 -8. And so that leaves us with a +5. Here we have manganese -8. Remember, each oxygen is -2 equals -1. So the manganese should be a +7. Here we have the dichromate. And so 2 times the chromium -14 equals -2. And so 2 times chromium equals -12. And so each chromium should be +6. And for this one, if we try it, let's see, so hydrogen's a +1. And so the carbon would have to be 8 divided by 3. Now the oxidation states can never ever be fractions. And so the 2 rules does not work for this compound. And so we have to use the Lewis diagram. And so we draw the Lewis diagrams. Now carbon's more electronegative than the hydrogen. And so it's going to get the bonding electrons. Now we just do the number of valence electrons for a free atom minus number of valence electrons for the bound atom, assuming the bonds are purely ionic. And so for the carbon, Here, we're going to start with 4 valence electrons for the atom, minus 2, 4, 6, 7. Now notice that, each line represents 2 electrons. And because you have a carbon here and a carbon there, they split those 2. So this carbon gets one of those electrons, this carbon gets one of those electrons. And so 4 minus 2, 4, 6, 7, that gives us a minus 3. Now if we look at the carbon in the center, we have 4 minus 2, 4, 6, and that gives us a minus 2. And so the carbon on the ends have a minus 3 oxidation state, and the carbon in the center has a minus 2 oxidation state. And so when you take organic chemistry, you'll find that the carbon in the center reacts a little bit differently than the carbon on the end, in part because of the difference in the oxidation states. Now in reactions, you'll often have a coefficient in front of a compound, and that coefficient does not affect the oxidation state. The coefficient will affect the total number of electrons being transferred, but it does not affect the oxidation state. And again, if an element is bound to something that is more electronegative, then the element's oxidation state is going to be positive. If an element is bound to something that is less electronegative, and so nitrogen is bound to hydrogen, nitrogen is more electronegative, hydrogen is less, so nitrogen's oxidation state is going to be negative.
A yellow solution of vanadium in its +5 oxidation state is poured into a large flask containing a zinc amalgam. The zinc serves as a reducing agent for the vanadium species. In the process, the zinc is oxidized to zinc 2 ion. When the flask is swirled, the vanadium changes to a light blue, indicating a +4 oxidation state. Swirling increases the contact between the zinc amalgam and the aqueous vanadium solution. Further reduction produces a deep green vanadium +3 solution. With even more swirling in the amalgam, the vanadium is ultimately transformed to purple vanadium +2.
And so this is a very cool reaction. What you have, vanadium is starting in a +5 state, +5 oxidation state, which actually is the noble gas configuration for argon. And then the zinc is losing electrons to the vanadium. And so the vanadium gains electron, goes to a +4, gains another +3, gains another, gets to the +2. Now each of these different oxidation states actually has a different color. Remember, transition metals can have a wide range of oxidation states. And so what we're seeing is the vanadium is being reduced and the zinc is being oxidized. Remember, Leo goes Gur, lose electrons is oxidation. So zinc is losing electrons, gaining electrons is reduction, and so the vanadium is gaining electrons. And so oxidation is the loss of electrons, reduction, gain electrons. Oxidizing agent is what causes the oxidation, and so oxidizing agents are reduced. Reducing agents are what causes the reduction, and so reducing agents are oxidized. And so a question you could see is, in the following reaction, what is being oxidized, what is being reduced? And so again, you have to determine oxidation states of all the elements and determine what is gaining electrons and what is losing electrons. And so if we look at it, copper here is by itself, so it's going to be oxidation state is 0. Here it has a +2 charge, and so the oxidation state is +2. Again, that coefficient does not affect the oxidation state. Now if we look at the iodine, here it's by itself, so it's 0. Now here, the oxidation state of iodine -6 equals -1, so the iodine must be a +5. And so the copper is losing electrons, so it's being oxidized. And the iodine is going from a +5 to a 0, and so the iodine is gaining electrons, so it's being reduced. Now you could also be asked how many electrons are being transferred. And so the copper, each copper is losing 2 electrons. And you have 5 copper, so 5 times 2 gives us 10. Now for the iodine, each iodine is gaining 5. you got 2 iodine in the reactions. 2 times 5 is 10. And so you have a transfer of 10 electrons. Now, it's very important to note that the number of electrons in the oxidation step is equal to the number of electrons in the reduction step, which is equal to the number of electrons transferred. And so 10 electrons in the oxidation half reaction, 10 electrons in reduction half reaction, 10 electrons being transferred. And so please remember Leo goes grr, lose electrons is oxidation, gaining electrons is reduction. Oxidizing agent is what causes the oxidation, reducing agent is what causes the reduction, and that the number of electrons in the oxidation step equals number of electrons in reduction half reaction equals the number of electrons transferred. I hope that was helpful.